gang. That was just a quick little video I just found online involving the Rubik's Cube, which I'm sure many of you have heard of before. And the Rubik's Cube is actually a neat little puzzle that involves a lot of patterns. You got different colors going all over the place, and there are actually tricks to solving it. And I kind of used that video to tie into what we're doing today for notes because we're going to be talking about patterns and inductive reasoning. So I like to relate a lot of this stuff to like fun things like, you know, Rubik's Cubes and puzzles and whatnot. So kind of bear with me as we go through these notes, okay? All right, here we go. Some key vocabulary. A conjecture is an unproven statement that is based on observations. Okay, so it's a statement that you can make assuming something, and we don't know if it's true, but we can say it because we've seen some kind of pattern forming. Inductive reasoning is a process that includes looking for patterns and making conjectures. Okay, it's kind of like in science class how you guys come up with hypotheses, so forth. That's what inductive reasoning is about. And lastly, a counterexample is an example that shows a conjecture is false. Now, with a counterexample, a lot of times I kind of relate that to lawyers, things like that, like logic. If you want to prove someone's false, you find an example or some kind of a way to prove that what their ideas are is incorrect. Okay? So we're going to be doing that later on. Number one, describing a visual pattern. Sketch the next figure in the pattern. Okay? So if we take a look at part A, what we got here is a box, 3x3 box. And I know it's hard to see here, but the pattern is these two, then these two, and then these ones going across. So you can see it's kind of rotating around. So the next one is again continuing to rotate. Okay, so if you had to write in a sentence what was going on there, you could say it's rotating clockwise, okay, 90 degrees each time. Alrighty? Very good. Part B, if we look from pattern 1, 2, 3, the next one, we'll notice that our base was 2, then 3, 4, so our next one should be 5. Okay, and then we're filling in the cracks. We basically got what appears to be like an additional row, okay, and we can continue to keep going forward with it. Oops, pardon me. Now, one thing about these as well, the cool thing about patterns in general, is that you can make assumptions for future events. So if I asked you guys to keep going with this, you could do that, okay, because you're looking at the previous material, which that right there is a conjecture, okay? Awesome. Number 2. Discover a pattern in the sequence of numbers and predict the next number. Okay, so something like this, what you guys are doing is the exact same thing with pictures, except now it's numbers, so now immediately you're thinking, oh, I don't want to do this, but it's still not as bad, okay? So for part A, 128, 64, 32, 16, we're going down. So when you're going down like that, you're either dividing or you're subtracting. So if you keep taking a look at it, all right, you'll notice that I'm subtracting 64 at first, then I'm subtracting 32, then 16. So there's no real set pattern there, but I am dividing by 2 each time. Okay, so predict the next number, 16 divided by 2 gives me 8. Okay? Now, part B, we're going from 5 to 4 to 2 to negative 1. We're subtracting 1, subtracting 2, subtracting 3. Now in this pattern, you can see that it's a gradual change. Okay, there's a simple little change. The next one I'm going to subtract 4. So negative 1 minus 4, okay, I wrote that kind of weird, gives me negative 5. Alright, you'll notice it keeps going in that way. Part C, now this is a tricky one. It happens once in a while. I'm going from 4 to negative 20 to 100 to negative 500. So you'll see the numbers are getting larger, but I am shifting from positive to negative and back and forth. So I'm going to multiply here. Think about what I have to multiply to go from 4 to negative 20. Well, not positive 5, but negative 5. So multiply by negative 5. There we go. Cool. So the next one, multiply by negative 5. We get 2,500. All right. 10, 20, 40, 70, 110. Plus 10, plus 20, plus 30, plus 40. So next one at plus 50 will get us at 160. Alright? So it's something as simple as this is a good explanation as to what you're doing. It will definitely help you on any upcoming tests or quizzes. Little group discussion here. Where do you notice patterns in your everyday personal life? Okay. Now, this is something that each of you can answer in your own unique way. Me, again, I'm a huge video game player. I play them all the time. I'm always using patterns. Like when I play Tetris, okay, you're looking for patterns to set up to try to get some like blocks to drop. If anyone's ever played an RPG, yes, for all you gamers out there, when you're walking around, you notice patterns when you're getting attacked or whatnot. Okay, even in Minecraft. Minecraft is a huge game. It's a wonderful game. I love playing that with my nephew, and he's very, very good at it. He beats me at it all the time. But in Minecraft, it's all about patterns. You're setting up different room locations, whatever it may be. Okay, so you can think about this as we go through this material. How do you see patterns in your own life? Okay, cool. On to the back. Making a conjecture. The sum of the first n even positive integers is what? Okay, so now when it says n even positive integers, this is a variable, okay, which you guys have seen before. My handwriting's terrible. I apologize. Positive integers and even. So we're saying like something like this. 2 plus 4 is what? 6. 2 plus 4 plus 6 is what? 12. 2 plus 4 plus 6 plus 8, 20. So these are the sums of our first n even positive integers. So we're going to make a general assumption, or give me a general overview. What do 6, 12, and 20 all have in common? They're all what kind of numbers? They're all even. Okay? And that's all we're looking for here. You're looking for even, odd, like what kind of like assumption can you make about the answers? Okay? Number 4, this is a little bit higher up. It's almost like a challenge problem, if you will. Okay. Again, terrible handwriting. Let's see here. 1 equals 1. Cool. 1 plus 2 equals 3. Now, the way they're rewriting this is 2 times 2, the quantity, 2 plus 1 divided by 2. Notice for the next one. 1 plus 2 plus 3 equals 6, which can be rewritten as 3 times the quantity, 3 plus 1 over 2. And as we go down here, you're going to notice that each line something changes. So what changes each time? Well, the 2, the 3, the 4. So that is our variable. All right? Everything else is a constant, the plus 1 and the divide by 2. Okay? So we're going to write out a pattern. You'll notice that the 2's change, the 3's, the 4's, so on. Instead of putting 2's there, I'm going to put a variable in. I'm going to call it n, since we talked about n in the last problem. So replace the 2 with an n. N plus the quantity, n plus 1, divided by 2. Now, let's just pause for a moment, hit the pause button. What we have here now is an expression that allows us to continue to make further observations. Okay, and what I mean by that is, we said from 1 through 6 here, you can find the sum. If you wanted to find the sum of the first 12 integers now, all you have to do, instead of adding 1 plus 2 plus 3 plus 4, all the way up to 12, is take 12, plug it into our formula, our expression over here, and we're going to find our answer. Okay? Like I said, a bit of a challenge problem there, just to kind of get you guys thinking maybe more towards like later half of the year. But it's good that you see that and get exposed to it a little bit. Okay, last part here, finding a counterexample. Here's the fun stuff. Show the conjecture is false by finding a counterexample. Anyone here like to argue? Okay, hopefully not too much, but when you're trying to argue, you have to try to make yourself look correct. All right, and sometimes when you're arguing against someone, you want to make them seem incorrect. So that's what a counterexample does. You're finding something that disproves the other person's opinion or thought. So for part A and for part B, conjecture. If the difference of two numbers is odd, then the greater of the two numbers must also be odd. All right? So what they're saying is this. 9 minus, let's go with 2, is 7. The difference, okay, subtraction, that's odd. Well, the higher number is also odd. So this doesn't disprove anything. This actually proves the conjecture that this individual made. Okay? Doesn't help us. But can we think of an example where a bigger number is not odd and the outcome when I subtract is odd? Well, let's try something else. 8 minus, let's go with 1. What's 8 minus 1? 7. Is my outcome, is my difference odd? Yes. Is the larger number also odd? No. This is a counterexample. Okay? You've disproven the conjecture. Now, how many of these do you think exist? If you're thinking infinity, you are correct, because no matter what, you can just keep rolling with them. I could say 10 minus 1, 12 minus 1, 14 minus 1, and you can just keep going. So the interesting thing is that for a problem like this, every single one of you in the classroom can have a different answer and all be correct. Okay? So don't think you have to write down 8 minus 1 to be absolutely right. Part B, conjecture the difference of two negative numbers is always negative. So again, I'm going to show you one where it doesn't work. Negative 2 minus negative 1. Negative 2 minus negative 1, this becomes negative 2 plus 1, which is negative 1. All right, that does not help disprove it. So I got to think of a different example. Well, let's try something like negative 2 minus negative 3. Okay, negative 2 plus 3 gives me positive 1. There's a good counterexample. Okay, so here's the one thing that's a little frustrating about these two. It's not like in a linear equation where you can just always, do the same steps over and over again, but you do have to just keep thinking about it. And as I always encourage you guys in class, just keep trying. Don't just quit on it. Eventually you will find an answer that makes sense. Okay, now if you've been checking out my webpage, I do have some links here. And the first link is for weather patterns. If anyone likes weather, stuff like things like that, meteorology. It's a field that, I know they're not always correct, but they do use a lot of patterns in figuring out what kind of fronts are coming in, how's the weather going to change, so on. Okay. I do have a link down here again for all my gamers playing Minecraft and using patterns. So again, it's a short little video. This individual was just showing how he changed up his different houses with his flooring, different things. It's all kinds of patterns. And lastly, how many in a row can you get? If you click on this link, anyone ever heard of the game Simon? Okay, where you have to do following the beats and following the pattern. I found a link online that takes you to that game, and I was curious how many you guys could get. I can never really get over more than 6. I'm terrible at that game, but I know some people are really good at it. So this concludes the video, okay, and you guys may begin the homework now and try that out. But again, if you have any questions, feel free to ask myself in class, okay, or Mrs. Long. And as always, good luck. We're all counting on you.